Okay, so I'll go back. So we are talking about Pursuit-Evasion Games just for sake of the recording because I have forgot. So introductions, we will have a Pursuit and Evasion, could be open and closed domain. We could have a continuous game and a discrete game. And application will look into the today's presentations. And we have a three type of scenario. The pursuer is faster than evader, or pursuer and evader has a or have equal speed, or pursuer is slower than evader. The whole idea, or I was fascinated about these games from the Chakravyuh point of view. See, if you look into the Chakravyuh, uh, so the person has some unique capability, it could enter or and can escape also. Uh, so how does it, if we want to, mm, okay, I have not shared the screen now. I'll share the screen. Okay. So today is two types of mistakes. One is in the recording, and another thing is the sharing. So now we are good to go. So we have to look into when the whole idea or whole my motivation was that we can mathematically formulate the Chakravyuh problem. Okay, and that's what today we'll discuss. So we'll see the simple things first. Missile guidance. So you can see this is a conventional guidance scheme, and we have a number of laws, that is a pure pursuit, line of sight, and proportional navigations. So in missile guidance, what we want, so if there is a target, okay, this is a, if you say target and this is a missile, it can have a velocity. Target could be moving or could be stationary. If it is a stationary, it will stay here, or it's a moving, it may be moving in a stationary line, or it may be moving in the uh, uh, it would be moving. I may have a little bit pause in sometimes because I am admitting the audience. So please bear with me. So it could be moving or it could be highly maneuverable. So what pure pursuit says, that see we have done in the optimal control. So if I write the
Excuse me, sir.
recycle,
Uh, Sir, your slide is not visible. We are seeing a different screen. Sorry to interrupt.
okay, so I'll stop sharing. I'll stop share screen again. So I don't know why what is happening. Can you see now?
Yes,
Pure
sir. Now it's visible.
Thank you very much. Aryans, I think you are Aryans, right?
Yes, sir.
Okay. So what happens now? Missile and target is there. So in pure pursuit, what the idea is that you have a tail-on chase. So we have looked into the optimal control, and I'll take a simple model, unicycle model. Okay, x dot equal to v cos phi, y dot equal to v sin phi. Okay, this is a unicycle model, and kinematics. We are considering the point mass model. And now I can have a phi dot equal to omega or a by v. So either we have to find the omega or we have to find the lateral accelerations. Lateral acceleration is like acting at that. How do we guide, okay, the missile that it intercept the target? So in the pure pursuit, what you do, you are doing the tail chase. So kind of you are trying to follow the each point of time target. If target is moving, you will, if you are here, you will try to follow this, you are try to follow this. So it's good, you get good results. We will look into that also. But what happens when you are at the end game, or you are able to intercept and target, do any maneuver, okay, so you will miss it. So we need some intelligent techniques. So there are different intelligent techniques are there. Okay, so this is the whole idea is shown for circle here, and there are line of sight guidance. So what you do in line of sight guidance, there are like a target, and you have a launcher and missile. So you maintain your like you ask your missile to maintain in line of sight. So as long as you are in line of sight, you are guaranteed to uh, intercept. So you can have a beam rider and command LOS. So only idea is that see you have a different tracking and the guiding radar. The difference is that again, like a pursuit, if aircraft maneuvers at during the interception or end time, you will require the high guidance. So in order to overcome this, in or in the missile literature, proportional navigation scheme is proposed. So it used the line of sight guidance law, okay, but it do something more than that. So what in the line of sight guidance law require higher accelerations when you are close to the target. So in proportional navigations, you maintain the constant bearing. So we'll see the idea, and it was like borrowed from the marine engineering. So it try to estimate what is your future position, and based on that you adjust the your heading, okay, and it is assumed that your velocity is higher than the target velocity. So graphically we want to see now what happens. See, if missile is here and target is here and target is slower, so this is called just sorry, so this is called line of sight, okay. Now next point, what you move in that stage, this line of sight in the relative frame does not rotate. And what happens, since you have a, you can derive the uh, equation for r, that is a relative distance. And if you make sure that this, there is an angle theta, that is a line of sight angle, this angle, if I draw the some local mm, local axis, and this angle you can say line of sight angle, in relative frame this theta does not change. If you can guarantee theta equal to 0, and if you ensure that r dot is less than 0, so that means this vector is getting smaller and smaller, you can guarantee the interception. So that is the idea of the PN guidance law. So how does it work? So you apply the command am is proportional to n theta r dot, and this is a this is the component alpha m. So here we have assumed the target is stationary, and this is a line of sight angle, and alpha m is a heading. So now I'll show you quick simulations. Okay, let me see if I can run this video. Just a minute, it was not showing here. Okay, maybe because it's in let me see, it does not show. Okay, so all right, I'll see if the future video shows. It has been not showing. I'll try to come back and I'll show that video during the end. So what happens, this is a classical, you can formulate this problem in the optimal control sense also, that is using the linear proportional navigations. So same things you can formulate it what we have seen the proportional navigations, but you can formulate in sense of optimal control what we have seen in the week 1 and week 2. Okay, now we are interested in differential games. Okay, when we say Pursuit-Evasion game, so it's a related, closely related with the optimal control. In optimal control we have a only single control that we are usually trying to minimize because we want to achieve some things with the minimal energy. In differential game theory, there are two control exist. Okay, two criteria. As we have seen in Pursuit-Evasion game, there are two player. One player want to that pay off what we have talked in the last thing. So if you say cost, now we don't say the cost function. Cost function we say usually when you have a single. So we have a payoff. One player want to minimize and another one is maximize. So for example, we'll take the what problem we have discussed in missile guidance. In missile guidance, what happens now? Missile will try to minimize the miss distance, and the what will target? Target will try to maximize the miss distance. Okay, so when I say miss distance, why we have to define the miss distance. So for in case if missile is carrying some warhead and it explodes at the time of the explosion, the distance we can define a miss distance that missile or pursuer would try to minimize and the evader would try to maximize. So it becomes the like kind of zero sum game where one player is trying to minimize the efforts and another one is maximize efforts. So it's a min max game. Okay, so that is what we have seen. This game can be played in a different way also. Now there are a lot of interest. So this becomes 3-player game. You can see there is an attacker and there is a target and defender. In this game, what happens? The attacker is trying to intercept the target, but there is a defender. Its job is that the defender will try to protect the target from the attacker, and the assumption is that defender has a higher speed or speed advantage over the attacker. So if you have a speed advantage, you can employ the classical guidance, but moreover they can cooperate and can pull the attacker or can take advantage of their cooperations. So this could be one set. Now we look into the like very interesting case here. In this case, what is that? We are assuming that both pursuer and evader are equally capable. They don't have a speed advantage. So when I say they don't have a speed advantage, see, if you have this unicycle model, so V is a speed, they have a same speed. Moreover, this UI, which is known as a lateral acceleration, or if I can say UI V equal to omega I, you have a same omega I capability. So one do not have or one does not have an advantage compared to the others. So what is now we define the problem statement, or we want to capture. So we say that we have some this minimum distance r minimum that we want to achieve if we want to be successful. So given configurations, if they are not, the pursuer is not close to the evader or does not satisfy the this one, so we have to find the feasible set of pursuit inputs that satisfy the capturability condition, that is a capturability conditions in some finite time. Okay, so that is the whole idea. So before I'll go now, if this game is played in open domain, okay, if its game is open domain, and if you have pursuer and evader, if evader just copy the action of the pursuer, if pursuer is moving the in the forward direction, or I define any direction, it if just copy the direction of the evader, the game will continue, the game will not end, and it's impossible to intercept the evader. But if the game is played in closed domain, it could be possible the pursuer can win. I am sorry, excuse me. Hmm? Or evader can win. So, so what we are assuming now, since both are capable, equally capable, we assume that at first that pursuer alone would be, single pursuer would not be alone be capable of capturing the evader. So, and moreover, the game will be played in closed domain. We have already talked about that open domain, it's not possible to intercept. So in order to formulate the problem, we use the idea from the computational geometry. So what we do the Bernoulli partitions. So what is this Bernoulli partitions? If I have a square, okay, some square or area is there. If I have a pursuer and evader, I draw the equidistance line. So the equidistance line, why I can draw? Because both have a equal speed. So in this area, any point pursuer can reach earlier than the evader. And in this area, any point evader can reach earlier than the pursuer. So that is the Bernoulli partitions. So what happens if the game is played in the closed domain? So for this set of the pursuer evader, we have this equidistance. This set of pursuer evader, we have this equidistance line. For this set of pursuer evader, this is equal, and we'll get this polygonal, okay, polyhedra. So if you see that red path is a safe reachable area for a evader. Why we are calling the safe reachable area? So pursuer can reach any point before the evader. So if we pose the game like that, if the evader reach at that point before the pursuer, it's winning. So that means it's a safe reachable area. Now, if I want to capture it, what I say that if initially safe reachable area is a non-zero, that means we have a finite area, and my pursuit strategy, if I drive that it, I make the area to zero, that means capture is guaranteed in the closed domain. So if that is a strategy, how do we do? So I'll write this area. If you Google it for any polyhedra, maybe there is a 1/2, I don't know. I don't remember. You'll get such formula. For any polyhedra, you can write this area of the that polyhedra. Now what I'll do, I'll compute the rate, change of rate of the area. So that is a difference. I'll use the geometric calculus dA by dt. So now what happens? It's depend on the gradient of the gradient of area with respect to the evader and the evader action. And if I have a more than one pursuer, so this is a summations and gradient with respect to the pursuer and then pursuer action. Okay, so I can write this. The whole idea is that I want to drive dA by dt negative, so the area becomes 0. So how can I do? What I do, if I individual pursuer choose their action in the negative gradient direction. So if you have done the Newton-Raphson's method or something, search algorithm or optimizations, so whenever you want to find the solution, what you do, you take the gradient and then you move in the inverse direction. So same idea is that, so that will become the square term, and whatever evader will do, okay, if there is a more than pursuer, the rate will be, because we are assuming that they are equally capable, so dA by dt will become less than 0. And then if I write at plus 1 is equal to at plus delta t dA by dt, if I integrate it, it's guaranteed that a will reach in some time 0. Okay, that is very simple idea. Hmm? So what now we have to compute the gradient. So this is, we'll take the help of geometry. I'll put up in the LOS direction. So LOS I have already defined when we connect the both point mass, that is the LOS, and then I put up in the perpendicular to that. I'll compute the area and do the approximations and put that limit epsilon equal to 0. I'll get the gradient. I'll do for uh, this case also. Perpendicular to the LOS in the, and I'll get the gradient like this. Now what is that? The we'll tell that we'll follow the simple guidance strategy, that is a pursuit strategy. So what that proposed strategy say, that if I the pursuer move the in the towards the center of the this boundary line or Bernoulli partitions, so it is guaranteed to that the will able to capture even there is a single pursuer and single evader in the closed length domain. So what I was telling, that in the open domain, if evader copy the action of the pursuer, it's not able to capture it. But now in the closed domain, even whatever evader does, if my pursuer moves towards this point C, okay, and if you see that YCI and XCI is a coordinate of the center point, and I am my heading, my direction is in that direction, so it's guaranteed to the capture. So for looking that, first what I'll compute the what is, okay, this is like a phi I is that, so I'll compute what is a tan alpha. Tan alpha is, that is a gradient. So we have seen in the previous slide, so the y component of x component, I'll get that. So I'll put this, substitute everything. Now I am computing the beta. That is a beta is computed for the based on this action. Okay. So what happens? I will find that my direction and that is a, we have a difference of the 180 degree. That means I am in moving in the inverse gradient direction. So now what I say, that this is a, like you can say, theorem of proposal. Under the proposed strategy, that is a pure pursuit strategy, the rate of change in the area is less than equal to 0 for any admissible evader control input. So that means whatever evader does, you do it. Don't. So it's, you do the best action. The rate of change is equal to 0 if and if only the evader follows the following strategy. So only things what, if evader moves in the gradient direction, only then it will be 0. So what is that? See, we will take for the single evader and pursuer. We know what is the pursuer action. So I have put substitute things and I'll get these terms. Now what happens? Uh, to make it 0, the evader has to choose this action, and if the evader choose this action, it will get this heading. So that means this heading is in the direction of the gradient, and our evader is moving in the inverse gradient direction, so it will cancel out and the area will change of rate of equal to 0. Now next, when we say that even dA by dt equal to 0, okay, That is the best the evader can do. It can maintain this DF, so your safe reachable area is not reducing. Even that happens, uh, the what is a pure pursuit, if we follow we can intercept that. So in order to show that what we have done, we have taken the r square, that is a r is a relative distance between pursuer and evader, taken the square, and then we'll take the time derivative, and so you will get that. So E dot minus P dot, you substitute that, and you look into that, you will get the less than equal to 0. Okay, so now less than equal to 0 is a tricky condition, because when it's equal to 0, that means what you are maintaining that. Okay, so we say that it is a less than equal to 0. Okay, and when will be it's 0? When r will be only 0. Okay, otherwise it will be not. Otherwise v is a positive number, and even r is 0. This is a positive number, so we don't have to worry. It is a guaranteed to be captured. So we'll look into the simulations. Hopefully simulations runs. Okay, in this case it's running. See, this is a evader, pursuer started here. This is a safe reachable area, and if you see that, okay, it's constant, and in order to make it 0, evader was also moving towards the boundary, but the pursuer is able to capture it. So now we come to non-holonomic systems. So whatever I have shown you, that works when the system is like a quadrotor. You can instantaneously change your orientations, or you have a holonomic systems. If you have a non-holonomic systems, in loose sense, if I want to understand the non-holonomic system, that means what happens? See, I have a turn radius constraint. It's like a fixed wing UAV. So if you are going into forward direction, if see evader is back, you cannot immediately change your direction. You have to take the circle. Okay, maybe Dubin's circle or things. So we cannot define this now safe reachable area where we wanted to define, because that was exploiting the property of the Euclidean geometry. Excuse me. Sorry. Really sorry. So what happens now? We'll take help of Dubin's distance and define the safe reachable set. So what is Dubin's distance? So if you have a minimum turn radius constraint, you will draw the circle. So it depends on the whether you are in the front direction or the back direction. If you are front direction, there is a no constraint. If you are in the back direction, you have to follow the minimum turn radius r, and then you will have tangent to the point. So if, for example, if you are here and your evader is here, so what will happen if your heading is here, you have to follow this path. So I'll draw the circle. Okay, and then you can have a tangent from this point. Okay, so this will be the path. So this is a Dubin's distance, and again, if look into the computational geometry, this is a optimal path or optimal distance. So you compute that set. Now the idea is that the pursuer is trying to minimize, okay, and the evader will be trying to maximize this area. And if you look into that, uh, this is a problem of the combinatorial optimization. Okay, so it's a min max game, and this problem are computationally intractable. Okay, so there are difficulty in the two level. First, I have already defined the set, that is give the safe reachable, but where it's since it's a non-holonomic, we do not have a closed form solutions, so computing its area is also difficult. Second, what is there? The problem is combinatorial. So how do we solve it? So we'll look into systematic how it can be solved. So what we'll tell, we'll cover the safe reachable area in an approximate way. So what we will take the example of this grids, where we'll see it in the computational geometry. Whole our workspace will divided into some regular grids. Okay. So in the regular grid, wherever evader is there, we'll take the evader Now with each pursuer, we check, okay, that what is distance using Dubin's distance, and then instead of checking for all the grids, so what will happen, see, I have this grid, I'll compute that whether evader can reach faster or pursuer can reach faster. Instead of doing that will involve lot of computations, I use the Dijkstra type algorithms that we use in the path planning. I'll start from the whichever evader grid, it will do in that grid whether the evader can reach earlier or pursuer can reach. Then what I'll take a two sets, open set and closed set. I'll take all the neighboring cell and I put into the open queue or open, you can say, set. Or from open set, I'll take one of the cell and I'll compute whether it's a safe reachable or not reachable. If it's a safe reachable, I put into the closed set and I'll keep doing for neighboring until all the neighborhood cell is a not safe reachable. So this is a quickly, and I can I have a, so the computational advantage, it will be like log 2n or type of the computation will be there. So once that separable area I have computed, now the whole idea is that what evader take the actions, so it's increase this area, and the what take the pursuer take the action, that is a it can minimize the area. So since the problem has a computational difficulty, what we'll do, we say that okay, we'll discretize our or parameterize the control action. We'll we will not have like a tabular method in the reinforcement learning or other. We'll say we have a finite number of control input only. So I have divided whole things, uh, u max u max by 2, 0, ux max by 2, u max. So only in the pipe, but you can take more things. The it will, and then the computational optimization have been converted into the sequential optimization problem. So what does it do? The pursuer will do, we will assume that the worst case, first one pursuer sequentially, it will take action to the minimized area. Then second pursuer will know the control input of the first pursuer, and then it will try to minimize the area. Then it's for next. So last pursuer will be knowing the all the control action of the all pursuer. Okay, but what happens, we'll assume that it to make the best game, evader will be knowing the all control action of the pursuer and it will choose that it's the evaded strategy. With that, what we'll do, we'll start, I think there is a video, we'll look into what will happen. We will start computing. So we have done this for two pursuer and one evader. The reason why we need here two pursuer, unlike the one pursuer in the holonomic case, there is a turn radius constraint. So when we look into this reachable sets, what will happen, because of our approximations, they are minimized, and because of turn radius constraint, this started maximize, then minimize. So this discontinuity caused the problem. So there is a difficulty in these formulations. So then what we say, okay, we'll take the idea of the what is a pure proportional navigation guidance law. We know that, okay, if it maintain the collision triangle conditions, so the best what can do, because pursuer and evader both are equally capable, if one evader or pursuer is low, so so what best it can do, the line of sight vector could be maintained to be 0, but relative separation between them is not decreasing because both has a same speed advantage. But the other pursuer, if it exists, it can take the advantage of that sorry, and can minimize this distance. So we look into this picture or this video. What will happen now, Blake is a evader and there are two pursuers, so you can see that the relative distance uh, is not getting decreased. But what happens, since the game is played into the closed domain, even the relative separation is maintained. The moment it turns, one of pursuer get the advantage and it intercepts. So what we have to hope now, if we divide the area, like if it is happening in the city that you want to shape, you don't want to launch the like a missile type of things or maybe anything. So outer area you have a high speed pursuer, but when you are want to safely play, you want to have equal speed. So there, when you employ multiple things, it can take a only turning example and the advantage while it turns, maybe in the few bounds it will capture it, but there is a not guarantee to this. So this gives us an advantage. So if you look into the, if you have seen the traditional Mahabharat, okay, so there was horses, okay, there was horses, and then uh, if uh, if you have a speed advantage, see, you would have a intercept the chain of the soldiers, and you enter into the go to another circle, smaller circles. But that is a some, this is a calculations. The key is that you should have a speed advantage. If you have a holonomic constraint, then you have to take advantage of the corners. So that is the message is there. Now we'll look into the case of high speed evader. That means evader is faster and the you have a slower pursuer. So can you do anything? So if you have a warrior like Arjun, can you beat them? Okay, or can you beat him? So that is the idea we want to look into. So what now we look into the safe reachable area. So if you see that safe reachable area, that is again compute from the numerical methods, it's come like this red line, okay. And then what we can do, we can approximate, this is like again like we cannot in the closed form we cannot compute, but we can approximate this is using the Apollonius circle. So Apollonius circle is a special circle where what is there, the evader and pursuer take the equal time to reach the boundary. So it's a trace of the points where the evader and the pursuer reach at the same time, although they have a different speed. So you'll take the speed ratio and will compute the this Apollonius circle. So it was originally proposed by Isaac. There is a famous book by Isaac on the game theory. You can look into that. And there was some work. They have proposed that using the Apollonius circle, if you make the perfectly encircle formation, it is guaranteed you can capture the evader. So my student Ramna, who is also like is the key in the conducting this lecture series, he proved that the result is has a false. Even we have a perfectly encircled formation, that means we have a check review. It is not guaranteed that we can intercept the evader. Okay, so what is this perfectly encircled formations? So if you have a one set of pursuer evader, this is Apollonius circle. So if you have a tangential, these tangential circles are there and you fill with the whole things. And you start with this geometry, the game. So if you think that you are come closer to the evader and you will be able to capture the evader, so that is not right. The moment you come closer to the evader, these circles become smaller because it depends on the your relative distance, and there would be a gap, and you can use that gap to escape from this encirclement. So I will not get into the mathematical details. Hmm. So this is a Apollonius circle. The locus has just minute, sorry. Excuse me. So if you take the ratio of Vp and Ve, you can get the Apollonius circle, and that geometrically we have solved. There are properties, and why we'll choose the Apollonius circle. So although the Apollonius circle is a subset of the shape reachable set, okay, the shape reachable set is a bigger, but Apollonius circle gives the problem or make a problem tractable. So this is a perfectly encircled formation what I have talked about. So I will not talk about now. Let's look into the result. Some. So I was talking about the gap. It can make a full. So see, it has been captured if it goes in that direction. So again, what is happens? The perfectly encircled formation, if pursuer is keep going in this direction, so evader will also come in this direction and the capture will happen. But what pursuer will, if wants to, or sorry, evaders want to pull you, it will come into this direction, and when grape is created, it will change the direction and it will escape. So let's see this simulations. So initially it's going here, and now what he sees, a gap is created, he changed its path, and now this pursuer cannot do anything. Okay, so that is what in the you can escape from the chakra view. So this was the strategy. But then you have to have a calculation. So I am amazed that our whatever in Mahabharata, or at that time they have that calculation looking into the relative position. They were fast enough to do that maneuvers, and they were fast enough to calculate these things. So I don't know, with computer we are still struggle, but they were really smart people. So you can look into different simulations. 6 pursuers we have done with the uh, and we look into the now different time. The good thing is that we can analyze, but now there is a no closed form solution, and there is a no guaranteed things. So when we have to look into the trend, we have to kind of do the Monte Carlo, or we have to run the lot of simulations, and then we have to look into what can happen. If we want to capture the evader, what we can do. So now you want to become like a drona, you want to ensure that, okay, no, I want to intercept the evader. So you say that I don't want to start with the perfectly encircled mm, formation, I will take overlapping circles. That means these circles overlap. The reason why you require this overlap, when you go closer, these circles become smaller, and if you go further, these circles become larger. So when you go the closer, still you maintain the kind of perfectly encircled formations, and when you are close enough, even there is no break in perfectly encircled formations, or the gap is small, evader cannot take advantage. So if you have enough resources, you can intercept the evader. Okay, and then we have this overlapping angle was calculated geometrically, and the whole idea, the problem is formulated that the evader will be trying to create a negative overlapping angle. That means the the gap is created between two circles, and pursuer will be trying to maximize the overlapping angles. So that means there is a more overlap. So if we play such a game, hmm, and this is a formulations, so that's minimization and maximizations. So I don't go into the details of this. You can, interested, you can refer to our papers. Hmm. Also, now we look into this. So what happens, see, now we started with overlapping circles, you can see into trajectory, uh, and see it escapes, it's create the gap. But if you have a large overlap, okay, so the evader is trying to create a gap. Okay, if even it may create a gap, it may not be possible to escape, because see, you have a good enough overlap, and it's get the intercepted. So mm, this is a story. So this is a traced path, you can see, and then we can look into the what is the like lambda. So this is about placement. Where will you put your the pursuer? Where will you put your evader? And what is their relative speed? Based on the speed, you have to put the your evader and the pursuer, and it also depends on the what is the radius of capture. So to prove that, we have done this type of simulations where number of pursuer is that, and what is the success, and the ratio of lambda is like a pursuer and evader. So what we can see that initially when have less pursuer, the success rate is not good as expected. When we increase the number of pursuer, our success rate increases, and it's see with the lambda, the speed ratio with the 65%, we have 100% success. Here is the 69. So this will give empirical way, or maybe you can say in tabular way, your success rate. So how successful, and based on this such analysis, you can compute the resources and you can employ, although it would be the expensive, huh? But you have a computations. Okay, and we have assumed that initial distance is 75 meters. The bad part is that for the moment you change the relative distance, you have to calculate the such distance. Okay, The good part is that now you can use deep learning algorithm to train such things. So with this, uh, I I'll I'll conclude my talk. So what we have seen, we have looked into the three types of the game today. One is your, like in the classical missile guidance happens, where missile has the advantage. The other one game we have looked into, both has equal speed, and there are two cases. One is a holonomic. If it's in the closed domain, you can capture it if you follow the center point. If it's open domain, good luck. We can't do anything. If it's a non-holonomic, we can employ more resources, but we don't have a good strategy. Okay. We have come with the two strategy, but the strategy based on the PN guidance, cooperative PN guidance law look promising. And when we have a uh, high speeding evader, we need overlapping circle type things. So that gives some insight how Chakravyuh can be created, intercepted, or escape. So thanks a lot. Now, if you have any questions, I am happy to take. Uh, so what I'll do, I stop recording.